stoichiometry. Let's see, using computer audio. Now I want to change that. That's good. Audio. Okay. Let's see. Are you still there? There you are. Okay. All right. Okay, let's line this thing up. Ooh, that gets both sides. Okay. And Felicia's present. Let's see who else shows up. Kaylee's been sick too. Yeah. So. We'll just carry on as if everything's normal. And we check the schedule. Refresh my memory. We're doing a review today. Yeah. Let's see.
I didn't get a chance to review much of this. We just got it on Tuesday. I just didn't get a chance yesterday much.
I'm trying to get the high points. So, solutions. Check. Looks like, yes, we did finish it. We'll look at some problems. Okay. So let me identify what we're doing. It's CHEM100, spring 2019, chapter 15, solutions. Yeah. Don't use that one anymore. Get one that works.
Here,
They don't last very long. Seems like we figure out how to make them work a little better. Maybe refillable or something like that.
right, that'd be nice.
That'd be nice if they had markers that you could, when you finished with them, you take them and put them in a docking station. And it refills them for the next time.
Yeah.
But then these companies wouldn't make as much money probably.
Yeah, I was about to say that maybe that'd be like $150.
Okay. So let's see. Let's see where we can what about that number one is a good one. How many grams of calcium chloride are needed to prepare 5.17 liters of a 0.5 molar calcium chloride solution? So the equation that governs everything that we're doing now is the definition of molarity. Okay. And we're given this part, 0.5 molar calcium chloride. And you can just assume these are aqueous solutions. We're also given the volume, 5.17 liters. So with that much information, we can find out how many moles are required of calcium chloride. But the question is, what's the mass required? So you can take two approaches. You can use a little algebra and create a formula that will spit out the mass in one calculation. Or it might be easier to find out how many moles you need, then convert the moles. But that's the approach I'm going to take here. So if we rearrange this one, the moles equals molarity times volume. And that's 0.5 molar times. You know, when we use the equation this way, that has to be in liters, right? I know I don't want you to be confused with the shortcut I took with the M1V1 equals M2V2. Because with that one, it doesn't matter what the volume units are because it's a ratio and they cancel anyway. Right. But when we're using this formula as is, it has to be in liters. And we end up with, get a calculator. Sometimes I like to do without looking at my cheat sheet just to see if I get it right. And I find mistakes that way too. 5.17. So I get 2.8, oops, nope, 2.58. 585 moles. Okay. So we got that many moles, and we just have to convert it to grams. And the problem gives you the molar mass, 110, 111 grams per mole. So I get, man, that's a lot. Oh, it's probably a lot because we're making a huge amount of solution, 5 liters. So I get 287 grams of calcium chloride dissolved in a final volume of 5.17 liters. And so when you start mixing this up, and that's going to be hard to produce, right, because you need volumetric glassware. So this is all theoretical, hypothetical, and never going to get that because we don't make glassware in fractionals. So, but this is just to see if you can do the calculations. If we were to actually prepare a solution in volumetric glassware, then the closest we could get to this would be a 4-liter flask. They do make 4-liter flasks. I mean, they're huge, but and expensive, but they do exist. And the reason you need volumetric glassware is because this volume is of the solution after you dissolve the solute, right? And that volume is not going to be consistent with just simply adding that much volume of water. It won't produce the same final volume. So it's important to use volumetric glassware when you make these solutions. What you can do, though, is make a concentrated solution. So we can make, well, I'm not sure what the solubility of calcium chloride is. I imagine it's pretty high. So let's just say, for argument's sake, you can make a 5 molar solution. And maybe 2 liters or 1 liter, something like that. Then you could take an alquat out of it and dilute it to another volume and end up with half molar. Okay. In that case, you would use M1V1 equals M2V2 to do the dilution. So then you would have the volumetric glassware probably available to do those dilutions without too much trouble. Oh, so that was number 1. Consistent. Okay. We'll just go to number 2. Let's just take another look at 2. Hi. Are you feeling better?
A little bit.
Good. So you noticed that I put your exam on Blackboard?
Yeah, I'm
Okay.
gonna be doing it today.
Okay, that's fine. Now, are you gonna do the PDF file and submit it? Because of course, all the bonuses require you to show your work if you want credit for it. So what you can do is I think I've got a hard copy I can get you.
Okay.
Let's say do it on the PDF, make sure control. There's one blank page, you can do it on the first.
Okay.
This could be overlooked.
Go.
Thank you.
You can complete the PDF file, and then you can attach separate worksheets to prove that you did the work, and that works for me too.
Okay.
Okay, so we just got through with number 1, and it's yes, it's recording. So we're going to move to number 2 now, and we're still using the same equation. Only in this case, the question is what mass? So we need mass of solute. For what? What mass of solute is contained in a volume of 64.1 milliliters of a solution that's concentrated at 2.00 molar? Okay? So like I said before, if you're using just this formula, that volume always has to be in liters. Right? So in this case, we'd have to convert this to liters. Just move the decimal 3 places to the left. There you got your polarity, your liters, and the material is sodium bromide. So they wrote it out, sodium bromide. So you got to be able to write the compound. Sodium and bromide. And sodium is +1, bromine is -1. That's all there is, just NaBr. And we're going to have to know what the molar mass is, because this is only going to tell us what the moles is. So then we're going to have to convert the molar mass. So we might as well do the calculation. Sodium is 23, 2 decimal places. And bromine is 7990 grams per mole. So this will be the molar mass of the compound, 102.9 grams per mole. We'll use that in just a minute. So now, if we're going to mass, we've got volume and molarity. We're going to solve for moles, like that. Then we're going to fill in the information that we have. 2 molar here, and volume is 0.049 liters. So that's 0.1298 moles, if I did my calculations correctly. Then we need to convert moles to grams, because the question is mass. That's why I calculated the molar mass ahead of time. So moles on the bottom here, cancel, grams on the top. So this will be 102.9. And now I'm going to have to use my calculator for that one. 2.9. So I get 13.4 grams of sodium bromide. So did that work? Yes. Okay. Any questions? It's always a good idea when you have a word problem to scribble down the information that you're given on one side, and then try to locate the information that's called for. Then that will tell you what formula, or sometimes more than one formula, is required to get the answer. So we can go from here and we say, okay, volume and molarity go together in what way? Well, that's a good place to start. Okay, so that was number 2. Let's see if number 3 takes us any further.
ABC.
I'm sorry?
It's one of those ABC situations.
Oh, yeah. Well, let me see. These ABCs actually have real chemicals associated with them.
Oh, okay. I just seen ABC.
And I think there's a lot of blue smoke in this problem. That's what I'm guessing. So let's take that, just see what we can do with it. Let's say you have 3 liters of 3.67 molar sodium chloride. Oh, that's called solution A. You also have 2 liters of 2 molar silver nitrate, called solution B. You mix those together, and that makes solution C. Okay, so there's not blue smoke. It's just we threw in A, B, and C, and it's really don't. Calculate the concentration in molarity of silver ions in solution C. Okay, this one is going to take some doing. Actually, it's not going to be too bad. So let's see, what are we getting? Well, we've got a sodium chloride solution in one. We've got a silver nitrate solution in the other one, and we're putting them together. So we've got a reaction. Okay. So sodium chloride is going to be added together with silver nitrate. Okay, those are both soluble. Then we put them together and something is likely to happen. So let's say, what we're going to have here is a double replacement reaction. In other words, you just swap the cations like that. So we put this one with that one and this one with that one and see what you get. So we're going to have sodium nitrate and silver chloride. We be sure we've got to write the compounds correctly. +1, -1, that's a polyatomic, so that's good. Silver is +1, chlorine is a -1, that's good. Now we need to look up, are they soluble? Right? So I know all alkali metals are soluble, all nitrates are soluble, so it's a double whammy in there. That means this is soluble. It's still in solution. So chloride, though, if you look it up in your chart, you find that silver and chlorine together make an insoluble compound. So that's going to drop out of solution. Right? That's where the reaction occurs, silver and chlorine. Okay, let's see if we've got it balanced first. There's one nitrogen, one chlorine, one silver, one nitrogen. So we're already balanced just like that. Now we can proceed. We've got our compounds written correctly. We've got a balanced equation. We can insert the information that's given. 3 liters of 3.67 molar sodium chloride, and silver nitrate is 2 liters of 2 molar. Okay. Now the question is what? Calculate the concentration and molarity of silver ions. Okay. Are we going to have any silver ions over here? Nope. Not free. They're going to be in that solid. So what we got to look for is, they're in solution over here. Do we have any left over of these silver ions that are not used up? Right, so that means we got to look for the limiting reactant. Okay. So in order to do that, we have to find out how many moles are here and how many moles are there. Then calculate product and see which one is the least, right? Just like we did with when we were given mass, convert to moles. But in this, we have solutions. Do the same thing, convert them to moles. Can't go anywhere in this equation without moles. So we know that based on this relationship, if we want to know moles, we just need molarity times volume. Molarity times volume. So all we have to do is multiply these two together. Right? So we got 3 times 3.67, and that's 1101 moles of sodium chloride. This one is easy. I'm going to put it down here so that we can draw it across. This one is 4 moles. This is sodium chloride, and this one is silver nitrate. Okay? So now to find out which one is the limiting reactant, you take this and say, well, what's the relevant product? It's the precipitate. So let's take this and make silver chloride out of it. Actually, it should be easy because they're all 1, 1, 1, right? So if you got this many moles of sodium chloride, then potentially you could have 11.01 moles of silver chloride. Sodium chloride makes the same amount of silver chloride if we use it all up. Okay? So this gives us 11.01 moles silver chloride. And this one gives us 4 moles of silver chloride. Okay, so which one's the limiting one? This one right here. That one runs out. So what does that mean to the problem? It means there are no silver ions left. They're all gone. We used them all up. So that's why number 3, the answer is C, 0 molar. There are no silver ions left. They're all gone. Okay? Now, if it had been the other way around, we would have used up a certain amount and had some left over. Then we'd have to just do a calculation and subtract. So maybe we'll get one of those in a few minutes. This is a good place to start because this gives you practice working with stoichiometry, moles, and limiting reactants without having to go too far with it. Okay, that was 3. Okay, just pick up 4. These seem to be going in some sort of logical order. 4. question is, what's the molarity of chloride ions? So we want to know molarity of chloride ions. We're starting off with a volume of 110 milliliters that has in it a mass of 3.22 grams of calcium chloride. Okay. In order to get the molarity, we have to convert this to moles, right, in order to use our formula. And this has to be converted to liters. Okay, 3 places to the left, 0.11 liters. We have to convert this to moles. And problem 1 gives you the molar mass, 111 for calcium chloride. Grams on the bottom, moles on the top. So 111 goes on the bottom, moles on the top. When we divide 3.22 by 111, I get 2.90 times 10 to the minus 2. 2.90 times 10 minus 2 moles of calcium chloride. Okay. But the question is molarity of chloride ion, right? Okay. So we have to know the relationship between calcium chloride and chloride ions. It's all soluble, so you're going to make 1 calcium ion and 2 chloride ions for every 1 molecule. Right? So this becomes calcium chloride to chloride. If the conversion is 2 to 1, you have 2 chlorides for every 1 molecule. So that means this is going to be 5.80 times 10 to the minus 2 moles of chloride ions. Now we can use the formula. We've got everything we need, moles of chloride in volume. And then volume. That'll give us our answer. Is that right? Yep. So I get, I'm going to use standard notation, 0.527 molar chloride. Okay, the closest one I can get to is C, 0.528. So that's the best answer. Okay? All right. Let's see if 5 takes us any further. What volume of dilution problem, number 5. Okay. The question is, what volume of 12 molar nitric acid? So we've got a molarity of 12 molar nitric acid. Okay. And they want to know what volume of that do we need to prepare another solution that is 6.71, excuse me, 0.1, excuse me, 0.1 molar, and the amount is 6.71 liters. Okay? We want to prepare this one from that one, so we better designate which which. So these are 1s, these are 2s. Now that we have our information up here, we know that this one times this one equals this one times this one. So now we can put our information in, or we can solve for V1 and then put our information in. Okay. The volume here is in liters, so our answer is going to be in liters, right? So M2 is 0.100 molar times that volume, 6.71 liters, and then this one is 12.0 molar.
I think I'll be at 30.
Those cancel, it gives us,
Till 2.
Okay.
let's see, 0.1, 6.71, and 12. So I get 5.59 times 10 to the 2. Liters. If we look at our answers, they're all given in standard notation, so we got to convert that. So that means 0.0559. Right, we got 10 to the minus 2 here, so we got to move 2 places over. 1, 2, 1. And we find that answer is A. Okay.
Got 98.8. What tall are you?
5'7.5". You know, I've said that for years. I don't know if I've shrunk or not.
All right, as long as we find something different each time, we just keep
What,
going.
the last day or the first?
Now, see, 6 is, it's like 3.
The 14th.
3 liters of 3.48 molar sodium chloride. 2 liters of 2.7 silver nitrate. Mix these solutions together and make it empty. Calculate the concentration of sodium ions in solution. Okay. So I probably should have put that up there. But it won't hurt to replace the equation. Sodium nitrate
118 or 64.
over chloride. Okay. Now the information that we're given is 3 liters of 3.48 molar sodium chloride. 3 liters,
Not that I know of.
3.48 molar.
Where I teach, but I don't think I'll.
Silver nitrate is 2 and 2.
The same thing probably that's still on there. I take a date.
Okay. Now what's the question?
Like a generic Claritin and my.
Question is, what's the concentration of sodium ion? Okay.
Nays and ebb every now and then if I'm stuck.
Sodium in this reaction is a spectator. Doesn't participate.
What it is with this leg.
Reaction being silver plus chlorine.
Or a
Gives
tendon.
silver chloride.
Like if I sit for long.
But sodium is an ion over here, and it's an ion over here.
I join the gym, and I try to do the
Okay. So you end up with the same amount of sodium
after I walk.
unchanged in solution before and after. So what's the difference? The difference is
I can do this in my
volume.
joints hurt.
Start off with so many moles of sodium chloride, but we're going to dilute it with this much volume. That gives you a different concentration, lesser concentration than you started with. So all you need is to recognize that this volume is total. These are the number of moles that you started with, same number of moles you end with, then you can calculate your molarity. So we just need this liters times 3.48 molar. That gives us moles of sodium ions, because for every 1 sodium chloride, you get 1 sodium ion. Right, it's 1 to 1. We don't have to make a conversion like calcium chloride or one of those others that has multiple ions. So if we calculate the number of moles of this, that's the same number of moles of sodium. So there's the number of moles of sodium. Now the volume is 3 liters plus 2 liters. Okay? Now let's see if I can do this. 48 times and divide by 5. And I get 2.09 molar sodium ions. Yep, it agrees with the answer sheet. Y'all can stop me anytime and we can pick up any one of these others. You know. So far, the first 6 have been sufficiently different so that we've learned something new with each one. When we get down to them where they're going to start repeating themselves, then we'll skip those. I'm probably going to regret erasing this thing. It'll show up again. Let's see what 7 says. 27.9 gram sample of HF is dissolved in enough water to give 2 times 10 milliliters of solution. The concentration of the solution, no big deal. It's just molarity equals moles divided by volume. So you have to convert HF to moles. And you need the molar mass of HF to do that. Then you have to convert the volume to liters. Then you can use your formula. So 7 is no big surprise. 8 is similar with strontium chloride. Let's see, what's 9? All right, so this gives you more information than you need.
David?
Given 3 different solutions, and it's only interested in solution 2. It wants to know how many moles of ions does solution 2.
Wait, okay. Hi, how are you?
So for number 9,
I'll have you sit right here for me.
I'm interested in solution 2. So we'll concentrate on this one, 68.7 mil of 3 molar. Ammonium sulfate. So you got to be able to write ammonium sulfate. Ammonium, polyatomic ion plus 1 charge. Sulfate, another polyatomic ion, minus 2 charge. So to make them balance, you need 2 of those. So, assuming you can write that correctly, now the question is, in solution, what's the concentration of ions? So, first of all, how many ions do you get out of this? For each one of these units, you get 2 here and 1 there. So you get 3 for the price of 1. So we can find out the moles of compound and convert them to ions. Right? The number of moles is molarity times volume. So we have molarity is 3 times volume is 0.0687 liters.
100 over 62.
That gives you the ammonium sulfate number of moles. But if we want to convert those to number of ions, we say for every 1 molecule, we get 3 ions. So it's 3 to 1. So for every mole of this one, you get 3 of those. That's why we multiply by 3. So if I say 3 times 0.0687, n times 3, we get 0.618 moles of ion. Oh, there. Wrong problem. So that's why number 9 is, the answer is E. Okay. Let's see, 10. Oh, this is just memory. A mixture of sand and water is what? Aqueous solution, solute, solvent, none of these. What is a mixture of sand and water? First of all, is it heterogeneous or homogeneous? When you mix sand and water, what happens? It's just, as soon as you stop stirring, it goes. So it's heterogeneous. It's not a solution. And only solutions are referenced as solvent and solute. So it can't be any of those. It's none of the above. Okay, trick question. Let's see about 11. Chemist needs 225 mils of 3.1 molar HCl. What volume of? Okay, we've done one of those dilutions already, so we won't waste any time on that. 12 is the dilution problem also. It's a dilution problem too.
Yes.
Determine the concentration of a sugar solution after you add the water. So that's like when we were calculating the concentration of sodium ions. You're adding a volume of water to the number of moles of sugar already there. We can dispatch this one pretty quick. So if you have 4 molar sugar and you have 250 milliliters of it, volume, that's molarity. And we want to know the concentration after you add. So the plus volume is 376.3 milliliters of water. Okay. So this is still the operative formula, only now that volume has to be total. Right. So we need to know the number of moles. How do we get the number of moles? Well, the number of moles is molarity times volume. And the volume has to be
Had a heart attack on the 9th.
in liters. Then we divide by the total volume. All right. So we have 0.2500 liters plus 0.3763 liters. All right. Move the decimal place. 1, 2, 3. A little over a third of a liter. So we just do the calculation.
The drain tubes.
Right. 0.25 again plus 0.376. So I get 2.28. Let's see if that makes sense. We started off with a 4 molar solution. We added 50% more water than the volume you already have. So we went more than double. the volume. So we should have in the neighborhood of half the strength. And we do 2.28. So it's a reasonable answer. Let's see. 13. No, I didn't get the right. I didn't get the same answer. I made a mistake somewhere. Let's see. Where's my mistake? 4 molar times this volume gives us the moles of sugar. Is that the question? Determine the concentration of sugar solution after the water. Yes. Okay. So that's set up right. How about this one? Is that right? 0.25 liter, 0.376. Okay, it must have been a math error.
I think you added 0.25 twice. I think you did 0.5 instead of.
Yes, I think you're right. Let's try that again. Let me do it in steps. What's a quarter of 4? It's 1 moles. And then added together with this one is 3, 6, 2, 6, 3, 7, 12.56. Yeah, there we go. That's liters. Maybe I keep myself out of trouble by doing it this way. 0.6263. That's better. 1.60 molar. Okay. Now, that was 13.
Yours answer 1.6.
Yes. Let's see.
Adam,
Okay. Let's look at 17. I know we didn't cover this with maybe 15 seconds worth of airtime at the end of the lecture on normality. Okay.
have a seat for me.
Let's do a little discussion of normality. Okay. We start from molarity. Molarity is the number of moles per liter. Normality, big N. So you have to be careful. That's why usually when you see it in print, they use an italic font, right, to separate it from nitrogen. Okay. The normality is by the same volume per liter, but up here you have the number of equivalents.
Any new surgeries?
Now we need to define what an equivalent is.
Does your chest bother you too? Says
It's usually,
it's just.
not always, but usually, normality is used in terms of acids and bases. Right. So an equivalent would be the moles of acid or base. Okay. So if you have, now, what do I mean by that? Well, if you have a reaction, let's say you were introducing hydrochloric acid into an aqueous solution, it's going to break up into those two, right? So for every 1 mole of hydrochloric acid, you get 1 mole of hydrogen ions. So this is an acid that gives you 1 equivalent per mole. 1 equivalent per mole. Okay. If we do this one, you get 2 hydrogens plus your sulfate. This is where you have 2 moles of hydrogen for every 1 mole of sulfuric acid. So this is an acid that gives you 2 equivalents per mole, right? So what's the relationship? Well, if we write the concentration of this side as 1 molar, H2SO4, that's going to be 2 equivalents per liter, which means 2 normal H2SO4. Okay? So 1 molar H2SO4 is 2 molar H2SO4. 2 normal, excuse me, 2 normal. It's 2 equivalents for every 1 of these. If we did this one, phosphoric acid, we would get 3 normal H3PO4. There's 3 equivalents for each one. Now, why do you even care? Well, for acids and bases, the net ionic equation for an acid-base reaction is that. Right? So if we know the molarity of our acid, the molarity of our base, we can easily make a mistake and say, if we only use this equation, make a mistake and say, all right, 1 molar sulfuric acid and 1 molar sodium hydroxide, they're not going to require equal volumes, right? The sulfuric acid will only take half the volume to neutralize that volume of sodium hydroxide because it produces 2 hydrogens for every 1. So if we use normality, then we can say, if we have 1 normal here and 1 normal there, then we would have equal volumes would neutralize if we have 1 normal. So how do you get 1 normal sulfuric acid? Well, molarity for sulfuric acid would be half that because it produces 2 hydrogen ions for each one. And if we were using phosphoric acid, it would be a third of that. Phosphoric acid would give you 1 normal, right? So if you have 1 normal, then you can say, if you say you're doing a titration, you want to find out where the exact point that you neutralize one with the other. Then you can say that this is analogous to our dilution thing. Number of normals, equivalents of acid equals the number of equivalents of base. And then this translates into here. If we solve this for equivalence, is N times V, normality times volume. So this would be normality of acid times volume of acid equals normality of base times volume of base. Okay? So it's, if you use this kind of thing, if you do these titrations every day, day in and day out, this is a useful technique. If you don't, then really all you need is the correct stoichiometry. Right? So rather than do it this way, we could pick it and do it this way. Say we were going to react sulfuric acid with sodium hydroxide. Well, sodium and sulfate would go together. Since sodium's +1, we need 2 of them to match the sulfate. And then we would make water with the rest of it. Right? So we need 2 sodiums, like that, which makes 2 OHs and 2 hydrogens, which means we need 2 of those. So let's see if it matches. 4 hydrogens, so 2 here, 2 there, that's good. 2 oxygens here. We don't count that one because it comes over here and translates exactly. And then 2 sodiums. So that's our balanced equation. Now, with a balanced equation like that, you can use molarity. Right? So you could say this is a half molar, and this is 1 molar. Then you can see that if you have equal volumes of each one of these, X liters. So let's use a real number. Let's say we have a 10th of a liter. 0.1 liter. Okay. So this one would be 0.1 times 0.5 is 0.05 moles of H2SO4. And this one would be 0.100 moles. Okay?
Shirley,
So, what's the ratio? Well, if we want to convert this one to that one to see if they're equal, right? You just say this one right here and do your conversion. So you have H2SO4 on the bottom, right? Sodium hydroxide on the top. So we have 1 of these, 2 of those. So 2 times that equals 0.100 moles. They're equal. So it's 2 ways of working the same problem, using normality with that formula, or using stoichiometry and doing it just the way we've always done it. I hope that proves that either one is effective. Let that sink in.
100.0.
Oh, I never did solve 17, did I? Okay. Now that we've got that preliminary discussion out of the way, we can go to the problem. I'm going to leave that there for now. Let's do, if I can create enough room down here to work the problem. So 17 says, determine the normality of a base if 93 mils of 1.8 molar HCl is required to neutralize 52 mils of it. Okay. So if we say that we've got 1.8 molar hydrochloric acid,
Are you allergic to anything?
and it takes 93 mils volume. So this is molarity, this is volume, and this is going to be in 0.093
Medical history.
liters.
Pressure and stomach issues.
How many equivalents does that represent? Well, since hydrochloric acid only makes 1 proton for each one, the molarity and the normality are equal. They're 1 to 1. So if we multiply molarity, well, let's do it this way. This is also equal to normality of hydrochloric acid.
Any surgeries?
And then the other part of the problem is we're neutralizing 52 milliliters of base. So they don't even say what base it is. It really doesn't matter. We're talking about normality. And normality references this equation. So it's talking about this one versus that one. So it doesn't matter where it came from. Okay, so for the base, this is acid. For the base, we want to know this part,
Which hip was replaced?
normality. And we're given a volume for the base of 52 milliliters. Actually, we're going to use that formula. We don't even need to convert it. Right? It's just like M1V1 equals M2V2. Milliliters will cancel.
Are you employed?
We can save ourselves a step by just using the milliliters. So in this case, what we're saying is the normality of acid, well, there it is over there.
History of anything. My sister.
So we can use that over here.
My half sister.
So the normality of the acid is 1.8. 1.8 normal times 93 milliliters equals normality of the base, which is our unknown,
Married?
times the bottom, 52 milliliters.
Any alcohol?
So we need 1.8 normal, 93 milliliters, and I got 52, and I get 3.2
Okay, sometimes I try to decaf.
normal for our base. Yep. Okay.
What's going on today?
Have this.
And
Just.
consequently, we don't even need to know what the stoichiometry is. If you know the normality, you can simply go to that equation. There it is. Okay. That's 17.
What pharmacy are you using today?
Well, I usually use CHEM100 because.
Let's see. Get something different here.
Okay, you can come with me.
Okay. Was that the next chapter? Because that problem 18, I have a sneaking suspicion we don't have what's required. No, we haven't done it. Okay, so 18 is extra credit. Okay. But you don't have the tools yet to solve 18. You have some of the tools, but we need the rest of them will come in the next chapter when we talk about gases. So 18 we just throw out for now. Let's see, 19 is a rerun. 20 is rerun. 21 is another. How about 22? Which one has the smallest number of ions? That looks like we need Henry Ford. How we do on time? 3:30. Okay, got an hour. Okay. So for this one, I set up an assembly line. We want to use the same calculation for each one. We just change the names to protect the innocent and calculate the number of ions from each process. Okay, so if we've got 1 molar sodium sulfide, okay, this is the first one, sodium sulfate. The key here is writing the formula correctly. Otherwise, you won't know how many ions are in that molecule. The next one is lithium nitrate. Lithium nitrate. See, lithium is an alkali metal, so it has +1 charge. Nitrate's a -1 polyatomic. So that's correct, just like that. Potassium hydroxide is 2 molar. Potassium hydroxide. That's +1, -1. And 2 molar iron 3 chloride. So this is 3 plus, chloride is 1 minus, so that means this one has to be 3. Okay. Now, first thing we do is find out how many moles. Well, let's see, how far are we going to go with this? We're looking for the smallest number of ions. So we really don't have to convert it to, we don't have to use Avogadro's number to say the number. Because if we get the moles, that's an expression of numbers. That's all we have to do, just get the moles of ions. We can do moles of formula units. All we have to do is multiply molarity times volume. Let's see, no, that's not right. We're just going to have a volume in here of, let's see where, here we go, milliliters. So the first one is 0.2468 liters, 5398. If you set it up, an assembly line, then you don't have to think it's hard. 0.1896 liters. Okay. So this is molarity times volume will give us the number of moles of the formula units. Now we've got to convert the formula units to ions. So we have, this is the formula. So that will cancel this part here. And then we need the number of ions per formula. You could write the compound in here, but I don't want to think that much. So for each one of these, how many ions do you have from here? 2 plus 1 is 3. Here you have 2. Here you have 2. And here you have 4. 3 plus 1 is 4. Now we got a problem set up. We just need to crunch the numbers. And the reason we have to do it this way is because you've got different concentrations, you've got different compounds, and you have different volumes. So you have to go to the trouble to do this calculation for each one. That answers the question. Okay, so 0.2468 and 3. So I get 0.74 moles of ions. And then we have 0.5398 to 1.08. And then we have 2, 0.305, 6, 2. So 1.22. And then the last one. 1.64. 1.52. Let's be consistent. Okay, so that says that A has the smallest number of ions out of all those 4. I guess, I hope it's a coincidence that they're in order. Any questions? Okay, that's 22. Let's see if we got anything different here. All right, we can do 25. That shouldn't take too long. Still got time. It's kind of repetitive, but not too bad. What you need to recognize here is that we're neutralizing acetic acid. And for acetic acid, the only hydrogen of interest is this first one right here. That's the acidic hydrogen. These hydrogens are bound. They don't dissociate. That's why they're written over here, and that one's written over here. This is 0.852 molar. And a volume of 6.89 milliliters. Okay. Then we have sodium hydroxide. And its concentration is 2136. And the question is, what volume to exactly neutralize this acid with that base? Okay. So this is 1 proton per, so this is also normal. And this is 1 hydroxyl per, so that's also normal. Same thing. Okay. So we can use our formula. So we can use the normality of acid times the volume of the acid. That's the normality of the base times the volume of the base. So really you're just plugging numbers. And since it's got volume on both sides, we can leave the milliliters as is. So this is 0.852 normal times the volume of 6.89 milliliters. And then the base normality is 0.2436 times our volume of the base. And just solve for the volume of the base. Now I get 27.5 milliliters. Let's see if that makes sense. Okay, this one is less concentrated than that one. So it's going to take more of this one to deliver the same number of hydroxyls as this one has protons at that volume. So that's reasonable. Okay. Do one more and do an actual calculation using stoichiometry. Ooh, 27. 27 might make your head spin around until you just stop and think. Look at what's given, look at what the question is, and approach it logically. So let's see if we can do that. So, what do you give? 100 milliliters of 0.25 molar sodium chloride. The volume is 100 milliliters. The concentration is 0.25 molar. And the final, this is the initial volume and concentration. The final volume, we don't know. But we do know the final concentration. which is 0.4142 molar. Okay. Now what's the question? How much water evaporated? Okay. You can't calculate directly, well, unless you do a little algebra, can't calculate directly what volume was lost. But what we're saying is, what's the change in volume from here to here? You had to lose some volume in order to increase the concentration from there to there, right? So we're going to have a difference of final volume. We're going to have a change in volume, which is always final minus initial. Okay. But we have to find out what final is first. Right? So we just say MI/VI equals N final, V final. Okay. And we're going to solve for the final volume. So that's MI/VI divided by final. So we have the initial molarity, 0.25 molar, times the initial volume. And we can leave it in milliliters because it's a ratio. Divided by the final molarity, 4142 molar. So this will give us our final volume. 0.25 and 0.4142. This is 60.4 millimeters is our final volume. So now if we say 60.4 minus 100,
Amber?
we get minus 39.6. That minus means that we lost 39.6 milliliters over that time period. Of course, the answer is
How old are you?
absolute value, 39.6. There. I just did that. I did it this way because whenever you say change in something, it's always final minus initial. So that's why they gave us a minus number. Okay, let's see. Be sure to cover all our bases here. Is kind of dredges up some procedures from the past. Talking about density.
Allergic to decimal cough syrup.
Should be interesting to try that one.
Taking medications daily.
I take Xyzal for allergies.
Okay. We have a nitric acid solution containing 71% HNO3 by mass, has a density of 1.42 grams per mil. Okay, we have to understand what that percent means. Because percent, I mentioned this number.
I had diarrhea and I was throwing up and I had a little bit of a fever. Yeah, and then this morning I woke up and I had a sore throat.
So let's see, what are we given? We have 71.0% mass nitric acid. That's what that means. This has a density of 1.42 grams per milliliter. what if we have 2.36 liters of that solution? Then the question is, how many moles of that formula unit do we have?
We don't have any units at
Okay.
that are open. You're gonna get her tested and everything. I have to wait out there till I get her in. I'm gonna put her in while I already know her results and.
How are we going to
Don't
prove
just come right
number
in.
of moles? Have the volume.
Yeah.
If we knew what the molarity was, we could do that. But I don't think that's the right approach. I think what we need to do is find out
I'm gonna have you guys sit outside and then I'll get you back in as soon as I can.
Thank you.
yeah. I think what we need to do is find out what's the mass of this that we have. Then we can convert it to moles. Because we can calculate the molar mass of HNO3. Let's see if we can get there. If this is 71%, let's go with what we have, 2.36 liters. What mass is that, right? Because this is mass percent, right? So what mass of solution do we have? We know the density of the solution, right? Density equals mass per unit volume, right? Grams per mil. So if we want to find out what mass we have, then we just say density times volume. So the density is 1.42 grams per milliliter. That tells us the units of measure that we need over here in volume. Actually, like that. Like this. In milliliters. So how many milliliters do we have here? 2, 3, 6, 0. 1, 2, 3. Milliliters. That'll tell us how much mass of solution we have. Right? 1.42, 2360. So I get grams of solution. Now we know the concentration of HNO3. So this is the total mass of the solution. We can find out how much HNO3 we have there because this one, grams of solution, can be converted. 100 grams of solution, grams of HNO3, right? So for every 100 grams of solution, we have 71 grams of HNO3. So that's 2.38 times 10 to the 5th grams. I think, oh, excuse me, a second. Forgot to divide by 100. That's only 2. All right. See the mistake I was almost going to make? So that's how many grams of HNO3 we have. Now we can convert that to number of moles. Like, wasn't that the final, what we were looking for? Final question?
Yeah.
Okay. So we need to know what's the molar mass of HNO3. Okay, hydrogen, nitrogen, I think. Yep. And oxygen, which is 3 times 16.
Stacy?
I get 63
Come get your weight.
grams per mole. So we divide this by that.
How are you?
Yep. CHEM100. This problem was really dimensional analysis, mostly. If you know one formula, that's it. The rest of it, we just use this as a conversion factor.
Sorry.
Yeah, I know.
Oh, okay, sure. Yeah, I'll post this today.
Okay, thank you.
Let's see, is that the answer? You got 37.8? Yep. Okay, we're good there.
100/62.
29 is, yes. Okay. Let's see, what do we got? Maybe
Now look at
25 minutes left? We're good at 30.
you still take singular.
Okay, so we got 23 minutes left. Let's look toward the end of these problems and see if there's anything out there that might have missed or are going to miss if we stay here. Look toward the back and see if there's anything. Okay. Looks like it's pretty consistent. There's one. And that would be good. Well,
I used to get a lot of times I've been off and on birth control because I've been switched to
62. We'll get to 62 in just a second.
I tried like pill. I haven't ever
Let's
tried
look
the
at it.
permanent like IUD. I tried the intrauterine, like the NuvaRing, insert take out yourself. I tried the pill.
Were they
Every time after my period and before I did, I would get the worst.
64?
I couldn't stand it.
When a solvent has dissolved all the solute it can at a particular temperature, you said to me, saturated. Yeah, saturated means full. Not less than full, not over full. Full. What if we actually can put more in there than you would expect saturated? Saturated, yep. And if we put less, unsaturated. What if we're unsaturated, but we do have a lot of solute in there, bumping up against saturation?
I was leery
That's
of
really
trying to
concentrated.
get a flu shot.
Yeah.
You know, I've heard.
You got just a tiny amount of solute.
She said honestly, she was like, most of the time, she was like, it kind of makes you feel like
Relative term.
but if you don't eat
Now we can look at 62.
That makes sense, right?
she was like, all of the birth controls have the side effects
Yeah.
anyway. And so I told my husband.
Okay. First thing,
I was like, anything, I was like,
We're giving 15 milliliters of 0.3 molar sodium phosphate solution. We're adding 20 milliliters of 0.2 molar lead 2 nitrate solution. What's the concentration of the phosphate ions left in solution?
But I was like,
Right.
I would rather get.
That's assuming that there are phosphates left. But we've got to prove that. So the reaction is going to be sodium phosphates.
But we don't know where people keep pressuring us about kids. We don't even know if we want to have any.
That's 3 minus, it's polyatomic ion. That's 1 plus, so we get 3 of those. And we're going to add lead 2 nitrate. So lead, and we're told it's a 2 plus with a 1 minus, 2 of those.
Yeah.
Now we're going to swap cations like that. The lead phosphate is here, and the charge didn't change. It's 2 plus 3 minus.
I'm gonna give you this urine cup. I don't have a room.
3 goes over here,
That I put you in. I'm gonna give
2
you.
goes over
I
here.
can't where the bathroom is and everything.
And you say 2 plus times 3 is 6 plus,
Where that
2 times 3 minus is 6 minus. We're balanced. Okay, look this up in your chart and you find it's a solid. That's the precipitate. And what do you have left over? Sodium and nitrate. That's definitely soluble. Yeah. Okay, now we need to balance the equation. Usually these double replacement reactions like this are fairly easy to balance. You don't even have to set up a budget. Usually. 3 sodiums, so we need 3 sodiums here. That means 3 nitrates. So you only have 2 nitrates here. So how are we going to do that? Well, we're going to have to say 6. Right? We're going to say 2. We're going to have to say 2.
And I wrote mine on 1. She's taking some sutures out. Okay.
Now,
Mine's
see,
on 1, 2 sodium hydrol.
you can set up a budget if you want. That's fine, just to be sure. 6 sodiums. Oops. That has to be changed. 6 sodium, 6 sodium. 2 phosphates. Ooh, 4 phosphates. What happened? Okay. When all else fails, do it the right way, right? So we got sodium, phosphate, lead, and nitrate. Let's see if I wrote these right. 3 minus 3, 2 plus, 3 minus, 2 plus, cross, okay, and 1 and 1. So we got to start off with 3 sodiums, 1 phosphate, 1 lead, and 2 nitrates. Here we've got sodium, 1 sodium, 2 phosphate, 3 lead, and 1 nitrate. Is that right? 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Okay. So if we do sodium, we'd have to have 3. That's where I went before. I wonder if I ought to go down here and do lead. Let's do lead. So if I put 3 here, that makes 3 lead and 6 nitrates. Okay? So if we go over here and make 6 nitrates, then that's 6, 6 nitrates and 6 sodiums. Okay. Now I'm going to need 6 sodiums over here. So I say 2 times 3 is 6. That gives me 2 phosphates. And we're good. So I probably ought to stick to my own rule book and not try to shortcut. Now we have a balanced equation. We can go to the next step. What are the quantities given? 62? No, 60. Yeah, 62. Here we go. 15 milliliters, 0.3 molar sodium phosphate. Phosphate. 0.3 molar. And 20 milliliters of 0.2 molar. And the question is, what's the concentration of phosphate? So we want to know the molarity of phosphate. Okay. This is 0.015 liters. This is 0.020 liters. So if we multiply 0.015 times 0.3, we get 4.5 times 10 to the minus 3 moles of that compound. And 0.02 is 4. times 10 to the minus 3 moles. That kind of thing. Now, we got to convert to our solid, because that's going to tell us how much of this is used and whether it's limiting or not. If this is limiting, then we'll have some of this left over. If that's limiting, then all of it's used up. So we need to convert this one to lead-3 phosphate. So we got sodium phosphate. Cancel that one. That's 2, and then 1 of those. Lead-3 phosphate. Okay, so that means 2 into this. 2 divided is 2.25 times 10 to the minus 3. Lead-3 phosphate. Okay, we convert this one, and here we're getting rid of lead nitrate, and we're going to make lead-3 phosphate. Okay, so that's still 1. This one's 3. So we're going to divide that one by 3. And that's 1.33 times 10 moles. Lead-3. Lead-2 phosphate, actually. There we go. Okay, so now which one runs out? This one runs out. So this is limiting. Excess. Okay? All right. In that case, you have choices. How much, okay, how much of this phosphate is used to make that? Okay. If this is going to be how much lead-2 phosphate you can make, that's how many moles, then how many moles of phosphate did you consume? Right? So we need to convert this to phosphate. So the compound we're going to cancel, and then how much phosphate does it represent? Right? So for each mole of compound, you have 2 phosphates, right? Because of the subscript, 2 phosphates. So now we can convert that to 2.67 times 10 to the minus 3 moles phosphate consumed. All right? That's how much we used to make this right here. How much did we start out with? Well, we started out with this many moles of the compound, but we've got 1 for each one. So we also have 4.5 times 10 to the minus 3 moles of phosphate supplied. So now we just need to subtract what was used, right? 2.67 consumed. So I get 1.83 times 10 to the minus 3 moles remain. Okay. Did I go far enough? He wants concentration. What's the concentration? So that's the number of moles that's left over in solution. What's the volume? Moles per liter. So we need to add this one plus that one. 0.015 liters plus 0.020. We add those two together, 0.015, 0.020 plus, and divide that into that value. You get 5.24. 10 to the minus 2 molar. Now, is it in scientific notation or is it standard? It's standard. So we got to move the decimal place 2 to the left. 0.0524 molar. Let me see which one that matches. It's like A. Okay. There are a lot of steps here. And it can get confusing, but you just got to take it one step at a time. You can't do anything until you get your balanced equation, which stumped me in the beginning. And once we got the balanced equation, then we say, all right, what do we have mixed together? Which one's limiting? And the limiting tells us if there's any of this left over. Right? Since that's limiting, that's excess, there is some left over. We just need to find out how much. So we got to go over here and say, all right, how much did we actually consume to make that product? Well, we already have this amount of product that we know is made. We just convert that amount of the formula unit into phosphate units by the ratio of 2 to 1. So that's how much was consumed. Then we go back and find out over here how much we started with, subtract the 2, and we take that and find out its concentration. So it's, if you back up and like take it methodically, you know, I know it's hard to do in the heat of battle, but the more of these you work, the easier it will be. I mean, you'll be able to, what do they say for combat soldiers? Get control of your adrenaline. It's the newbies that walk into battle for the first time that just completely fly apart. I mean, they lose it. But the battle hardening is that process of going through battle several times and you learn to control things, assuming you live through each battle, right? So, similar idea, but this is not life and death. Okay.
I'm gonna drop his book.
I think I covered, yeah, I think we covered all the topics that we're going to need.
The rest of it.
Yeah, the rest of it is repetition of the types of problems we've covered today. With that one exception, which we X'd out. I don't know how that one made it in there. I wasn't paying attention, and the authors probably thought they were being smart about sticking that one in there. Well, let me see. Hold on a second. This is chapter 15. Yeah. Oh, yeah, that's the problem. 15's out of order. 13 is gases. So they're expecting us to go to 13 first. That explains it. But I think solutions, for some reason I wanted to take solutions first. I thought it fit better with the previous chapters when we get the gases. I'll show you how to work it anyway. Okay? So unless you have any questions, we are done for today.
Whenever you open up PDF, it keeps trying to open it up in a new window. So you have to right click and then click save. And then when you pull it up, I had to open, right click and click open with Word document. That way it opened up in Word, and then I clicked Enable, and it took it a minute to like download or do something. But once it did that, I was able to go into the edit it. I just went to the line, wrote my answer. And then if there was one where I needed to show my work, I just went beneath in the blank space and just typed it out. I didn't do like the actual formula. I just wrote this times this and this times this.
Yeah. I mean, if you open it up in Acrobat Reader, you can actually fill in the multiple choice answers, but you can't edit it. So that way,
Yeah, my
you convert it to,
very difficult.
if you convert, you convert it to Word like that, then you can also put your work in.
Yeah, 'cause I wrote out the balanced equation here.
Mm-hmm.
And then just rather than having to do all the steps with the parentheses, I was like, that'll be way too hard. So I just wrote it out word by word.
Yeah, and I understood it.
Cool.
Strange as that may seem.
Honestly, that problem took me longer than most